The armature consists of a set of insulated copper coils wound around an iron core. The armature conductor flux interacts with the flux in the main field created by the main field poles, and that results in a production of mechanical torque. The torque drives the motor rotation and power output. A commutator consists of a cylindrical component made of multiple segments, usually constructed from conductive material like copper. Each segment is insulated from the adjacent segment and is connected to one end of the armature coil winding at the riser. The riser is the perpendicular extension of the commutator segment. When the motor is connected to a power source, the direct current flows through the brushes, which make contact with the segments of the commutator. As the commutator rotates, the brushes maintain the contact with the segments. There are three types of commutators: molded, banded, and V-ring. I believe a molded comm is not repairable and is typically replaced by a V-ring commutator. Here I'm showing two commutator styles, a glass banded comm and a V-ring comm. With a banded commutator, the segments are restrained and held onto a core with a resi glass band. After the segment pack is assembled on the core, banding grooves are cut. Banding is then wrapped around each groove at 600 psi. Glass bands should be coated with Viton, which seals the banding. Viton is a blue color substance and is tacky, and therefore the Viton should be then layered with Limitrack to prevent collection of carbon. This picture shows a technician installing banding around a banded commutator. V-ring commutators are available in a wide range of sizes, from 2 inches to several feet in diameter. Appropriate to most applications, the V-ring commutators can have different riser styles to accommodate different size and coil configuration. Unlike the banded comms, V-ring commutators are designed with a copper and mica segment pack retained from the inside. The interior of the segment pack assembly is cut into a dovetail. A steel assembly including a spool and two caps for either end is then used to retain segment pack. Matching angles on both caps fit into the cut dovetail angles of the segment pack, insulated by mica V-rings, and they form a clamp. V-ring commutators close with a nut at the outboard end are normally seen in the range of 2 inches to 12 inches, and larger units use bolts to secure the steel. And here's the dovetail. It's pictured showing a 3-degree and a 30-degree angle. Here we see individual copper segments and mica segments. Remember, there's a mica segment between each copper segment all the way around the commutator. This segment, mica, includes a low resin content. Mica acts as the insulator between each copper segment and to avoid that shorting out of the commutator. This mica segment has a dielectric strength of 600 volts per mil. That's about 24,000 volts bar to bar on an average comm. In V-ring comms, there is a design gap between the steel cap and the copper bar on a 3-degree angle of the dovetail. This is included to allow differential expansion of the copper and steel in operation, and it's a necessary component. The riser can be open or closed. Open allows air to flow through the riser area. The airflow performs two functions: cooling and carbon clearing. In the closed riser design, air does not flow through this area. Instead, it flows around to a different path, which is behind and over the riser. The riser can be solid, meaning the riser and the segment are machined from the same stock material. The riser can be inserted, meaning the riser is machined separate from the segment, and then inserted into the segment and brazed. An inserted riser avoids a lot of material waste during segment manufacture, therefore lowers the manufacturing cost. And another is a lap joint design. The separate riser is brazed to the copper bar with shape to match the trapezoid shape of the bar. This image shows insulated copper armature coils inserted into core slots and ends connecting to the commutator at the riser. Here's an example of what a typical armature coil may look like. The armature coil pitch or coil span is equal to the distance between the two adjacent poles. It'll be the same regardless of what type armature winding is used. Coil pitch is equal to the number of slots divided by the number of poles. If this is not a whole number, it's rounded up. An example might be a 4-pole motor with a 25 armature slots. The coil pitch would be rounded to 6. DC motors are wound with different coil configurations. Two type configurations are the lap and the wave wound configurations. And the difference in configurations have to do with how they are connected to the commutator segments. With lap windings, coils are under the same pole pair and are connected in series. Wave coils under one pole pair and are connected in series with coils under the next pole pair, which makes the shape appear as a wave. And here's some differences between a lap winding and a wave winding. In a lap winding, the number of parallel paths equals the number of poles. In a wave winding, it's always 2. And the lap winding requires equalizers, and wave winding does not. Lap winding may be used in a low voltage, high current application, where a wave winding is mostly used in high voltage, low current. And we'll understand more about this terminology later in the other lessons. The coil span is equal to the distance between the adjacent poles. So in a 2-pole machine, the coil sides are 180 degrees apart. In a 4-pole machine, they'd be 90 degrees, and in a 6-pole machine, they would be 60 degrees. That coil width and that coil pitch is always the distance between the adjacent poles, no matter if it's a lap winding or a wave winding. We said earlier in wave windings, the number of parallel paths is always 2. There will be 2 brush arms holding brushes, no matter how many field poles there are in the motor. In a lap winding, there are the same number of brush arms as there are field poles. In a lap winding, the number of parallel paths is always equal to the number of poles, and also to the number of brushes. Lap winding has many parallel paths, thus it's more suited to high current, low voltage DC machines. In a simplex lap wound winding, the ending point of one coil is the starting point of the next coil. Here we see how the coil sides connect to the adjacent comm segments. The blue coil and the gray coils help us identify the connections. One of the coil sides is connected to the lower portion of the riser, and the other coil side is connected to the upper portion of the riser. And we can see the ending point of one coil is the starting point of the other coil. Here's another illustration of the finished end of a coil connected to one segment and the starting end of the adjacent coil joined to the same segment. And that happens all the way around that armature. A simplex lap wound DC motor, the armature is a series of coils. However, when we install the brushes, we have parallel circuits. In a 4-pole motor, we have 4 parallel circuits or parallel paths. When voltage is applied to the armature, current will flow in the parallel paths. It is extremely important that the current in each path is the same. If the flux from all the poles is exactly the same, the current carried by each path will be equal. However, there's always a slight unbalance in EMF in the various parallel paths due to variations in air gap, length, or difference in magnetic properties or pole material. As a result, conductors used under stronger poles generate greater EMF and hence carry different current than the remaining conductors. The current distribution at the brushes become unequal and result in circulate current in the brushes. Equalizer coils are commonly connected in commutator bars having a circumferential spacing about the commutator based on the number of poles. For example, the span would be 180 mechanical degrees for a 4-pole machine and 120 mechanical degrees for a 6-pole machine. Armature windings can be equalized many times, such as every third coil. Here's an example of equalizers installed every third coil. Equalizer coils provide a low resistance path between commutator bars so that circulating currents flow through the equalizing circuit rather than through the brushes. This is a General Electric factory equalizer pack. Equalizers are installed on one end and in some cases both ends of the armature. Here the shop is installing their own equalizer jumper. Here's the equalizer pack installed on the commutator end of the motor, and the picture shows the connections made on the risers. They're made below the coil connections. The more parallel paths there are, the more difficult it is to have each carry the same portion of the total load. For this reason, 4 or more poles use equalizers. This armature has equalizer coils installed on both ends.